Okay, so we'll continue talking about 4D. So 4D means three integration, triple integration. So that is the case. So calculus generally people know single integration. Single integration means there is one independent component and one dependent component. So that is a single integration. Now, if there are two independent, so that is 2D. 2D in the sense that there are two components, one independent component and one dependent component, y equal to fx. So everything lies in a plane, x and y both in a plane. Now, z equal to fxy. So if there are two independent components and one dependent component, and everything are orthogonal to each other, if that is the case, then it is 3D. So two independent components in a plane and then one dependent component that is orthogonal. So all are orthogonal to each other. So it constitutes 3D, 2D, 3D. Now we'll talk about 4D. 4D. So 4D, 4D cannot be drawn. So 4D cannot be drawn. So how we can draw 4D kind of the scenario. So better before drawing it, better we understand what is 4D. Okay. So suppose that I have a cube. I have so okay x boundary and then y boundary and then z boundary. So I have a cube. So cube has three independent components x, y, and z. Okay. So if there are three independent components, then certainly we are not talking about the cube itself. Okay. We are talking about the independent component. Dependent. So what could be dependent on three dimensions? Means I can understand that if there is an area, if there is a surface, then dependent component is vertical one. So vertical one would vary here and there the way we vary the x and y in the xy plane. I mean fxy, if xy varies, fxy vary. If fxy vary, then this vertical would also vary. If vertical varies, then we get variable height 3D. Okay, but how if three components, okay, so volume component, if three component changes. Now earlier the points in area was changing, that is x comma y. Now point in a volume is changing, x comma y comma z. All three are independent to each other. If they change, the what can be the fourth component? Okay, this is a detective movie. Means like you don't know what is the fourth component. If that is the case, then can we consider the fourth component as density? Density. Density in the sense that the fourth component, which is function of x, y, z, is density of the cube. Okay, so if that means whatever we are talking here is not written in any book. Okay, you can try. So whatever we proceed, okay, smaller thing when we talk about one dimension, two dimension, three dimension, it's all right, but in four dimension you will get for four dimension, but whatever the explanation, the reasoning behind the scene that we are placing, probably it would not be available anywhere else. Now, anyway, so now question is arising that if the fourth component we consider it as density, okay, how much dense the cube is at whatever the places are. Okay, so if this is the cube, if this is the cube, suppose this is the cube, then if this is the cube, then when x comma y comma z equal to 0 comma 0 comma 0, that is at origin. So okay, so if that is the origin, so if this is xy plane and this is z, then here at the origin of the cube, so there what is the density? And slowly at each point in 3D, what is the density. Suppose the density is x plus y. So if I take or x plus y plus z, let me make it simple. X plus y is the density. Now wherever I take the point, I just check what is x and y. I don't check the z. So whatever the x and y, if I add x and y at that point, density I know. So density along the z axis at any x and y in this case is constant. Or if I take x plus y plus z, then everywhere density is variable as function of x, y, z, that is x plus y plus z. If that is the case, then the density at origin is 0, means there is nothing there, null. Otherwise, it grows, and density at the right, far, and top, okay, that corner density is maximum. So this is 4D. 4D in the sense, now I have a function over xyz, fxyz, fxyz, and that function is nothing but density. Consider like this. Okay, so this is four dimensional. Now if it is four dimensional, so we are getting the function that is based on x, y, z. If it is four dimensional, and if we want to calculate the net density, if it was three dimensional, then whatever the function we used to have, that was fx comma y. So z value is fxy. Fxy, that is the height. Fxy, if this is xy plane and there are points on the xy plane, for each x comma y, there is a fxy. Fxy into underneath the area is the volume. So we were calculating the volume, net volume. So integration is nothing but the calculating the net amount. If I have rate of change of the amount that is available, then integrating gives the net amount. So here, if fxy is the variation as per the area, then fxy dx dy gives us the net volume. fxyz dx dy dz, fxyz is a function dx dy dz, where fxyz, now we have to consider out of the 3D. So that is, we consider it as density function. So what is the density at xyz? So if I integrate this, putting three integration, triple integration, one for dx, one for dy, and one for dz. If that is the case, then we are calculating the net. Okay, so if I have density is kg per meter cube, then we are calculating the net weight. That is integration. Integration is nothing but, if I have rate, density means what is the volume, what is the mass per unit volume. If I have, that is variation as per the xy is concerned. If I take fxyz equal to x plus y plus z, anything I can take, 1 plus xyz, 1 plus x into y into z. So if they are 0, then at origin at least I have one density. Otherwise, it is multiply of x, y, z, or 1 plus x plus y plus z. So at least at origin, I have something. So if I have fx, y, z, in that case, then that is density per kg per meter cube. If that is the true, then fx, y, z, dx, dy, dz, if I integrate three times, triple, one for dx, one for dy, one for dz, then it comes as net weight, kg per meter cube. So meter cube gone away in the integration. So rate what we are seeing in the integral equation, rate comes to mass. Like we always talked about number of kilometer a person is collecting per hour. So per hour gone. How much number of kilometer he collected at the end of something. Now, what is the limit value? So first limit, if I take dz, so dz first limit will be in, now fxyz equation I have to place f braces x comma y comma z, that is function over x y z. So if I put 1 plus x into y into z, if this function I have taken, dx, dy, dz. So if I multiply dx, dy, dz, it will come as dv, d volume. Okay. So function into d volume. So that is the integral I have to find. So d volume is nothing but dx, dy, and dz. Now, since z is, if I take z first, dz first to integrate, then its limit should be in function of x and y. If I take dy next, then its limit should be in function of x. And if I take dx at the end, the outermost limit, then it should be constant. So innermost limit should be in function of two outer limits. Then middle limit should be in function of the outermost limit. Outermost limit should be constant. So this is how, this is called density function. Okay. So now can we go back? Can we go back? Now you remember very well that we had taken of a semi example of a semicircle. If this is semicircle, then if I place in xy plane, then the z value, you remember the z value of the semicircle. So if this is semicircle, the z value, so this is x-axis and this is y-axis. So this is x-axis and this is y-axis. If that is the case, then this is xy plane. And z value, it is y. Means if y is 0 here, then z is 0. As y grows, then z grows. So that becomes a kind of a 3D. We were finding the volume of the 3D. So 3D. Okay, so we'll talk about the another aspect of density function. Now we have we have 2D. If I take only surface x and y as independent component, not the z like in 3D, okay, then it is 2D. It is a surface x comma y. If it is 2D, then can we consider we said fxy equal to y. So fxy, if y grows, then fxy grows. Fxy equal to y. Fxy as a density function. These are not available in any book. So fxy as density function. If it is a density function, then I am talking about a plane only. Okay, one plane, not 3D. One plane where each point in the plane has separate density. If this is x-axis and this is y-axis, then along x-axis y is 0, so density is nothing. As we go along y-axis in this semicircle, then density starts increases. If that is true, then density is per square meter. If that is true, the density is kg per square meter. If that is true, then if I try to get the total weight of this 2D, not 3D. Now life is easy, right? If if I go for kind of okay, so if I go for calculating the weight of this 2D where the fxy is density function, then it is fxy dy dx, fxy dx dy, where fxy is y. Now, if I calculate dy, then limit would come in the variation of x, 0 to square root 9 minus x square, and then x is minus 3 to 3, because we had taken radius as 3. No need to go for z value. I mean, it's a matter of understanding that net equation will be same because we have to find the same result. Rather than saying what is the volume of this, I can say what is the weight of this. Okay, so weight is, this is better explanation, because integration is nothing but the function is rate of change. Function is rate of change. So if it is a density, then it is kg per meter square. And if that is the case, then dx into dy, that is the area. So that is the per meter square. So kg per meter square into meter square, we are trying to find the weight of the plate. Simple. Okay. Now let's talk about fx equal to fx. X is this is x-axis. This is x-axis. Now along the x-axis I have independent component, that is x. Then there is a dependent component called fx, that is y. So if this is x, then this is fx, y. So this comes at 2D plane. Now for each x I have fxy. Height into width I get the area. If I have a rate of change. So fx, the x-axis is single dimension, but if you go for fx orthogonal, then it comes to 2D. Can we make it as 1D only? So if I have x, then fx is density, kg per meter, because it's only one dimension, right? Kg per meter. So at the beginning, what is the density at each point? Okay, so kg per meter in the sense that if x is 5, if this is x axis, then this is origin 1, 2, 3, 4, 5. If x is 5, at this point, what is the density? Fx. X, fx. If I know the density, then if I do fx dx and integrate over to constant, then I get the total weight. Kg per meter square gone, because fx dx meter cut out. So we can understand this integration with the density function. These are not mentioned in any of the book. Okay, so now we understand the integration as far as density function is also concerned. So if I have one independent variable, then my calculation, now there are density, it is thinner here. If I take density is 1 plus x, then at x equal to 0, density is 1. So as it goes, density is growing, x is growing. So here the density is high. Now if I calculate the total weight of this rod, that is the integration. Or if I take y f equal to fx, this is up to you. You make 1D into 2D and calculate the area, or let it as 1D only, and whatever the function we have along the independent component fx, that dependent component is density. Then just integrate it and get the total weight. If it is 2D, then x and y are independent component. It is a surface. Let it be surface only. And whatever fxy we are getting, consider is at density, not z value. So if I consider it as z value, then I get to calculate the volume. If I consider it as density, I get to calculate the total weight. But we are remained in a 3D, 2D only. But if I consider this as fxy as z, then we calculate the net worth. Now we'll come to 4D or 3D, whatever. So if I have a volume and then I have fxyz, then fourth dimension I can consider as density. Now I have to consider it as density because there is no fourth dimension I can imagine. X, y and z. So three axes are over. So in that case, if I have fxy z, then it is density 1. We can grow in this fashion to nth component also. Means in there. So now if I have 4 dimensions, then fifth one I can consider by meter 4 or something like that. Now if I need to calculate the weight of the volume, then we have to do fxyz, dx, dy, dz and triple integration. What if I with now if I need to calculate the volume, not the weight, if I need to calculate the volume, not the weight, then I have fxy, not fxyz. In that case, z equal to fxy. In that case, dual integration is suffice. But if I want triple integration to be used as calculation of the volume, can you tell me the answer? Now I have a volume dx, x, y and z, three independent components. If there are three independent component, then fxyz function over x comma y comma z, then that is the density. If that is the density, then dx dy dz, that is the volume. Fxyz dv, if I calculate this integration, it leads to the weight of the volume. Fxy dx dy, where fxy is the density, it leads to weight of the surface. Fx dx, if fx is the density, then it leads to the weight of the line, rod. Okay. Now, question is, can I use fx, fxyz dx dy dz triple integration to calculate the volume, not the weight? Simple question. Answer is, we can calculate, but fxyz has to be density. If that is density, then net will be the weight, not the volume. We can convert weight to volume if fxyz is 1. Fxyz is not in a function of xyz. It is not variable. It is 1. So density is 1 everywhere. If that is the case, then whatever the weight we are calculating, that is the volume. So with triple integration also, we can calculate the volume. You can think same thing in fxy and fx, where we are calculating the area and the length. Okay, so here with triple integration, we can calculate the volume also, not the weight, even though we have density function at fxyz. Now fxyz is one constant everywhere, at to origin to right, okay, far and top corner, everywhere its density is 1. If density is 1, then fxyz dv, that is dx dy dz, fxyz is 1. So the triple integration of 1 into dx dy dz, or triple integration of dx dy dz or dv, okay, where z is limit in the function of xy, and if I calculate z first, and then y is a limit of function in the limit of is a function of x, and then outermost limit x is a constant. In that case, this will give us the volume. What else you want? Okay, this is one explanation. Now you remember that if this is the surface, this is xy plane. This is xy plane. If this is xy, if this is xy plane, okay, if this is xy plane. Now let's go back to fxy equal to z. If fxy equal to z, then we were trying to calculate the volume through fxy dx dy double integration. So in that case, the fxy, whatever we are getting, so that we were integrating with the dy first and dx next, or dx first, dy next. If I integrate through dx first, then limit has to be in function of y. If I then I integrate dy, then limit has to be in function of nothing. It should be constant. So outermost is constant, inner is in function of the next outer, all the outer integration. So that is the concept of the integration. But what we considered is that if I do dx first, then dx is nothing but xz, independent and dependent. Z is dependent, x is independent. So xz plane, we have so many, in xz plane, we have so many areas. This is what we are doing. Now, these areas are in, if I do dx first, fxy dx dy. So fxy dx is calculation of the area in xz plane. So whatever area we are calculating, that area is in function of y. Now that whatever we get, now we have to integrate over y. What it means? It means that if I have an area at any particular y, I have another area at any particular y, I have another area at any particular y, I have another area at any particular y. So if I integrate fxy dx in the function where limit is in the function of y, then y will be in the calculation of fxy dx, y is constant for a particular y we are calculating. Now, if we place the limit, then x, wherever the x variable is, that will be modified to y. Like fxy dx, and fxy is y, then y dx is yx, and the limit is whatever the limit we are placing. So, if this is xz plane, the limit of x will be from this side to this side. Okay, so if this is plane, then plane's left side and plane's right side. That is minus square root of 9 minus y square, if 3 is the radius, to square root of 9 minus y square. Because if this is semicircle we had taken, in the semicircle equation is x square plus y square equal to radius square. So x equal to 9 minus y square. So minus 3 what we have seen here, that will become minus square root of 9 minus y square. 3 what we are seeing will become a square root of 9 minus y square. So fxy dx is y dx yx, and where minus 9 square root 9 minus y square to 9 square root 9 minus y square. So it will come as y 2y, okay, square root of 9 minus y square. Then again I have to integrate with the y, and where the limit is 0 to 3. Now what we are doing. So when I say I have calculated the xz plane area, so that came as 2y square root 9 minus y square. 2y square root 9 minus y square. So at each y we have different area. Now, but if for each y, if I substitute y value 2y square root of 9 minus y square, that came when I calculated in xz plane. So for each y, I have area like that. But if I substitute y to some value, so for this is y, if this is y and this is x, for each y, I have the area value. So this is simple scalar value. If I calculate for each y, then it will leads to another surface. Can we see yz plane? So in another surface yz plane, at each point we have calculated value, that is 2y square root 9 minus y square. So now I have, so this leads to another surface in yz plane. If there is another surface in yz plane, for that equation is 2y square root of 9 minus y square. Then for this surface, I just need to integrate with the dy to calculate the value. That will come as net as volume. So fxy dx, what we get, that is the area, okay, that is the area of in xz plane. But for each y, that is a scalar value. Okay, if that is a scalar value, then that scalar value will fall in yz plane. For in yz plane, at each y we have a z value. We can consider like that. Okay, if that is true, then that z value into dy is the area of that surface. So finally we get the volume. So this is how the intricacies of the integration works. So one surface we get in the equation of y, then for each y we have a z value, then that leads to a surface in yz plane. Then yz plane, to calculate the area in yz plane, then we have fxy, earlier we can call it gxy. Gxy equal to 2y square root of 9 minus y square. So gxy dy, and then we integrate. So we get area along yz. So we got area along xy plane, xz plane, and then that area, then we calculated yz plane, it becomes the volume. Now, if I am going for 3D calculation, I mean 4D calculation, where fxyz is density function and it is not 1. If it is not 1, then what all surfaces we are calculating? So if fxy is z, then we calculated the xz first, and the area of the xz plane first, and then that area became a part in the yz plane, and we calculated everything. So xz and yz, can we see something? One is independent when one is dependent. In YZ also, one is independent and one is dependent. These are the planes. In 3D, now it is not a plane. Okay. So what I can consider. So if I go for single integration, fxyz dx. Suppose this is what I'm going first. So dx into fxy, what we are getting, it will calculate an area where the independent component is x and dependent component is fxyz. Now you have to imagine something. So if this is a kind of a diagram, this is a 3D model. If this is 3D model, and at each point density is different. The density versus x-axis, x-axis versus density. Whatever surface is coming, that is a kind of imaginary surface. For that you are calculating the whatever area comes, okay, those values again next I am calculating dy. So whatever the value comes, that value will be part of the density y plane. First we had independent and dependent that constitute a surface for which we calculate the area. So first we calculated, okay, so first we calculated for the dependent component, that is density and x plane. It's easy, clear. If you imagine it, that for x-axis, what is density and x-plane? If you understand that, then you are calculating fx, y, z, dx. Whatever comes, then again density versus y plane. So this is y, then density versus y plane. If that we calculate, the next item we are calculating. Whatever, so first is fx, y, z, dx. Whatever is comes, consider it is as gxy. So gxy into dy, so density, next density, whatever comes. So it will be per meter square. Earlier it was per meter, so per meter q or something like that, it will come as per meter square. So gx is kg per meter square into dy. So that whatever surface you are imagining, so that surface we are calculating. So now it will come as kg per meter. Now that, so consider fx, gx and lx. So now lx dz. So lx next density with dz. So whatever the surface you are imagining, that surface again we are calculating the integration, and that would lead to final weight. If fxyz is 1, then density is smooth everywhere. In that case, we are calculating the volume. Okay, I believe this is heavy. Okay, so the idea was to take the example, okay, whatever we are doing in the semicircle. So if I have semicircle, and in semicircle, okay, we were calculating the now that if this is semicircle and it is a plane, and fxy is y, okay. Now we have z as separate, so we are trying to calculate the volume. So if I'm trying to calculate through the volume through density function, the density function is 1. If it is 1, then fxyz dz, now z is in variation of y. This is what we are saying. So in that case, z should be integrated prior to the y. X we can keep anyway. So 1 dz, if I integrate over 0 to y, it will come to y. So y dx dy, it comes to same story what we did earlier. If I integrate it, as now we are calculating the volume through density function, fxyz dz dz dy dx. If that is case, then fxyz is 1. If that is the case, then z limit is 0 to y. If I calculate y next, then y has the limit from 0 to a square root 9 minus x square. Then x has limit minus 3 to 3. Okay, if I do dx calculation, so fxyz is 1, dx first. In that case, then x has limit minus 3 to 3, that will be converted to minus a square root 9 minus y square root 9 plus 9 minus y square, minus square root 9 minus y square to square root 9 minus y square. So if I calculate this, then after that I can calculate the dz. So dz is in variation of 0 to y. So this fx y z dx, it came in a function of y. Okay, then I integrate with it with dz, or I can integrate it. I have to integrate with dz because dz is dependent upon y. So if I integrate the dz, then z will come into the picture, and then I have to limit 0 to y. If that is the case, then net will come as a function of y. Now dy and integrate with 0 to 3. Okay, so integration of dx, dz and dy, that is also called dv, dvol. So that we can do in any combination, depends upon who is dependent upon whom. So z is dependent upon y, so dz will come prior to the dy. That is the only prerequisite. Otherwise, if it is not the case, then we can do any permutation combination. Okay, so finally we understood that through density function is also a way to calculate the integration. But if we come to density function in kg per meter cube, then it is considered as 4D. In that 4D, we have to calculate the net weight where the dV is dx, dy, dz. Otherwise, we can consider the in 2D or 1D not going with the independent component as orthogonal as a density function only. So no need to go beyond one level, and 1D where we have one independent component, it will be calculated as 1D. 2D as two independent component will be calculated as 2D, and 3D, okay, one there is a kind of 3D where three independent components are there, it will be calculated as 3D. So that is concept of a kind of density function. So for the 3D, if we have 3D, then equation is fxyz dx dy dz. If density function is in variation of xyz, then we are calculating total weight, or if it is 1, then we are calculating the total work. Okay, so that is the scenario. We will proceed probably with few more examples before we land up into a spherical coordinate, radial coordinate, and kind of cylindrical coordinate, and little bit we'll see more, then we'll wind up. So kind of the integral calculus, but consider me that it is kind of done one. So means we'll see few examples and then we proceed.